Fine. Today we'll start a new part of current electricity. In our previous lecture, we have studied about current electricity. Today we'll start another second part of current electricity. That means Kirchhoff's law. In this part, we'll study what are actually Kirchhoff's law. And Kirchhoff's law govern the conservation of charge and energy in an electric circuits. So for Kirchhoff's law, we have to understand about the junction rule and closed loop rule. In our previous lecture, we have studied about the Ohm's law for current electricity. Now we will start the Kirchhoff's law. First of all, what is Kirchhoff's law? To know about the Kirchhoff's law, first of all, we have to understand about the basic concepts of connection law. So connection law, that means a branch, loop and globe. So first of all, what is the branch? That means a branch represents a single element such as a voltage source, electric source, or a resistor. For example, we can denote the branch for this. There are three types of resistance here. Actually, first one is 5 ohm resistance, 5 ohms, then twice ohms, okay, then thrice ohms. So this is and the electricity in the right one 2 ampere, and in the left one the voltage is 10 volt. So this is actually a parallel connection. So it represents a branch of electric source. It is called actually example of branch. So a branch represents a single element such as a voltage, just a single voltage source, an electric source, or a resistors. Okay, this is a what branch. Now next one, what is the node? Node. A node is the point of connection between two or more branches. So node is the actually point of connection between two or more branches. If we connect many branches, two or more branches, then the connection point will be called node. So suppose 5 ampere and 5 ampere, 2 ampere, 3 ampere are parallel connection. So you can join these like this: 5 ampere to B point, and 1 point of 2 ohm and 3 ohm will be another point C. So this is called actually loop. Okay, so the whole rectangular circuit can be written as a this curve way. Okay, so this is called actually node here. Now what will be the loop? A loop is any closed path in a circuit. That means loop means what? Any closed path. That means the both connector ending and the in an electric circuit, first terminal and last terminal will be closed. Then it will become closed circuit or closed path. So an independent loop is one that contains at least one element not contained in another loop. Okay, it will contains only at least one element not contained in another loop. A network satisfies the fundamental theorem of network topology. That means branch, loops, and nodes minus one. Okay, so branch equals to what? Loops plus nodes minus one. This is actually fundamental theorem of network topology. So first of all, we have to remember about these branches, loop, and another one is actually node. So to now we are coming to Kirchhoff's law. So first of all, you have to know about the branch. What is branch? Okay, then node. What is node? And this is the example of nodes. and what is loop. Okay, this is the actually properties of a loop. Okay, now what is the actually a Kirchhoff's laws? There are two types of laws according to the properties of electric current, open or closed. So there are two laws. First law will be current law of Kirchhoff's law. First law will be current law of Kirchhoff's law or junction rule. The algebraic sum of electric current at a junction in any electrical network is always zero. Okay, suppose at any point of a electric wire there are many ways of electric current. Suppose I1, I2, I3, I4, and I5. Actually, at this point O, the all coming algebraic sum of electric current at this point will be always zero. That means what? I1 is entering, this is why positive, and I2 is outgoing, this is why negative. Okay, and I3 also outgoing, I3 also negative, and I4 is entering, so positive, so and outgoing will be minus. That means all this sum will be zero. That means algebraic sum of electric current at any junction in any electrical network is always zero. So for this sign convention, the incoming current towards the junction are taken positive, and the outgoing currents are away from the junction or taken negative. So outgoing currents will become negative and incoming will be positive. You have to remember this. The charge cannot accumulate at a junction. The number of charge that arrives at a junction in a given time must leave in the same time in accordance with the conservation of charges. So this is very important laws of Kirchhoff's law for conservation of charges. Now, this is the actually first law for Kirchhoff's law. Actually, this is the for open or current wire, electric current. Now for another law, this is second law is called actually voltage law or loop rule. Okay, you must know what is loop. The algebraic sum of all potential drops and EMFs along any closed path or closed electric wire in an electric network is always zero. That means this is potential drops, okay, or EMFs, and EMFs along any closed path in an electrical network is always zero. Now, if we consider this electric circuit, suppose there are two E1 and E2 electric drops or E and EMF, okay, and electric current I1 coming from E1 and I2 from E2. There are two sources, okay, and there are three resistance R1, R2, and R3. Okay, now there are A, B, C, D. There are all are connected with each other. Now A and C directly connected. That means AC means what? I1 plus I2. Okay, I1 coming from E1 voltage and I2 coming from E2. This is why at this A point will pass through I1 plus I2. This is the direction. Now, if we consider ABCA, that means there are two closed circuit. This is the one loop, and another loop is ACDA. Okay, there are two loops. So for the first loop, ABCA, we can write outgoing. Okay, E1 electric current outgoing I1 from E1. This is why minus E1. Okay, minus E1 plus plus at B point, what will be? I1 R1. Okay, because electric current coming in R1, this is why I1 R1, then plus I2 R2 into I1 plus I2 into R2. You must know from Ohm's law B equals to IR. That means electric potential drops or and drops equals to B equals to IR. This is why we are using this one at point A, at point for the point for AB, this, and for AC will be this equals to 0. Okay. Now for another loop, A, C, D, A. Okay. So what will be the algebraic sum of all potential drops and EMF? First of all, coming entering I1 plus I2 into R2. This is the electric drops, potential drops, and this will be negative because this is outgoing from second potential difference E2, and minus I2 R3. I2 meeting with resistance R3. This is why I2 R3. At this point, potential drops will be B equals to IR. I means what? I2 and R3. Then meeting with what? EMF E2. That means positive. So this will be negative, and this also negative, and this will be positive because electric current outgoing from the EMF 2. So this is actually second law. It is also called voltage law for loop 1. Sign convention, the EMF is taken negative when the traverse from the positive to negative terminal to the cell through the electrolyte. The EMF is taken positive when we traverse from negative to positive. Okay, negative to positive terminal of the cell through the electrolyte, and this is according to cell and sign convention. The potential falls along the direction of the current in a current path, and it rises along the direction of opposite to the current path. So you have to remember this one. The potential drops or falls and potential rises will be according to the sign convention. So the potential falls is taken negative and potential rises will be positive. So you have to remember that there is a footnote. The path can be traversed in clockwise or anti-clockwise direction of the loop. You must know anti-clockwise is positive and clockwise is negative. This is the actual explanation for the second law of the KIRCHHOFF'S law. Okay, now we'll discuss now the historical background of KIRCHHOFF'S law. KIRCHHOFF'S law are two equalities that deal with the current and voltage in an electric circuit. We have seen this. So they were first described in 1845 by a German physicist, Gustav KIRCHHOFF'S. This is his biography. Now, Ohm's law by itself is not sufficient to analyze circuit. Why we need actually KIRCHHOFF'S law? Because Ohm's law cannot describe the circuit analysis sufficiently. This is why we have to use KIRCHHOFF'S law. When it is coupled with KIRCHHOFF'S law, we have a sufficient powerful set of tools for analyzing a large variety of electric circuits. And KIRCHHOFF'S current law is based on the law of conservation of charge. Okay? And KIRCHHOFF'S voltage law is based on the law of conservation of energy. KIRCHHOFF'S law can be applied to AC circuits in the same way as for DC circuits, provided we use phasor sums rather than algebraic sums. Okay, actually this is the this is why we have to use KIRCHHOFF'S law here. Now KIRCHHOFF'S law states that the algebraic sum of current entering to a node or a closed boundary is 0. Actually, we have described what is node. That means I1 is coming and I5 is outgoing, I4 is coming entering, and I3 also entering, and I2 outgoing. So in that case, a node, A is the actual node here. Okay, so a node is using to describe this first law of KIRCHHOFF'S, which is law of current. KIRCHHOFF'S law of current. So before applying Kirchhoff's current law, sign convention is very important. The following sign convention, current entering node will be what? Negative, and leaving will be positive. We can also take entering positive and leaving negative. So applying Kirchhoff's current law with sign convention, we can denote this: minus I1 plus I2 minus I3 minus I4 plus I2. Because entering means what? In this example, negative, and leaving means positive. This is why we can denote the Kirchhoff's current law in this way. So Kirchhoff's current law can be written also I1 plus I3 I4. That means I1 means entering, all entering currents equals to all outgoing, sum of all outgoing currents. So all sum of all entering currents equals to sum of all outgoing currents. So alternatively, Kirchhoff's current law also can be stated that the sum of the currents entering a node is equal to the sum of the entering leaving of node. Okay. Okay, now explanation of Kirchhoff's voltage law. That means second law. Kirchhoff's voltage law states that the algebraic sum of all voltage around a closed path is zero. To illustrate Kirchhoff's voltage law, we can consider this circuit. R1 is the first resistance, R2 is the second one, and V is the voltage drop or EMF. So for this, you must know by Ohm's law, B equals to IR. Okay, here series connection. This is why electric current will be same. Okay, same. This is why here the voltage drop will be BIR1, and in the second resistance, voltage drop will be IR2. So sum will be what? IR1 plus IR. If voltage drop across the resistance are termed as B1 and B2, then we can write B1 plus B2. Okay. So in series connection, total voltage. Furthermore, BS minus B1, B2 equals to also 0. That means this shows that total voltage is sum of drops across each resistance, which is known as Kirchhoff's voltage law. This is actually explanation of our second one. So mathematically, we can Kirchhoff's current law can be written as summation n equals to 1 to capital N IN. That means entering all sum of all current equals to 0. Algebraic sum of entering current equals to algebraic sum of outgoing current. Sum of outgoing current. That means for a node, I1 entering and I4 outgoing, I3 outgoing, and I2 entering. In that case, we can write this one. Where n is the number of branches, here n is the number of branches, and in is the nth branch current entering or leaving of node. Similarly, Kirchhoff's voltage law can be expressed as M equals to 1 to capital M, where capital M is the elements. Okay, we already defined what is loop, what is node, and what is branch. So sum of all algebraic sum of all voltage drop and EMF equals to 0. This is actually figure for that. Actually, we have to use this one actually for mesh analysis, loop, mesh analysis, planar circuit, non-planar circuit. In that case, you have to use our Kirchhoff's law. So the Kirchhoff's current law states that the sum of the current entering and leaving a node is equal to 0. That means you can convention method, summation of all, then will be the sum of all currents entering and leaving. Okay, this is the example. Suppose I1 equals to 5 ampere and I5 is 3 ampere and I4 is equals to 2 ampere and I3 equals to 4 ampere. So in that case, entering sum of n equals to capital N, all entering and leaving electric current equals to I1 entering, this is why positive, and I2 leaving or outgoing, this is why negative, and I3 also negative because outgoing, and I4 also negative because outgoing, and I5 is entering, this is why it is positive. So this whole sum will be what? Whole sum will be 0 according to the first law. Now, that means we can write the sum of currents entering a node. A node is equal to the sum of current leaving the node. That means we can write summation entering current and sum equals to summation of outgoing current. That means for this example, we can write I1 plus I5 equals to I2 plus I3 plus I4. So we have to remember, now we'll describe an example, an important example for KIRCHHOFF'S law. Now we will discuss an example of KIRCHHOFF'S law. Suppose there is a closed circuit. First one, first EMF E1 equals to 3 volt. Here, first resistance R1, 2 ohm, and I1 is coming to at P. This is actually junction or loop or node. So P at P point, I1 is coming and I2 is also coming from second EMF, second source of electric current. Now R3 is the third resistance. Though, so another resistance R2 and I2 is also coming here and I2 is here. Okay. So now we'll try to find out the value of I1 and I2, I3. We have to find out, we have to find out the value of I1, I2, and I3. Okay. So according to the first law of electric, Kirchhoff's law for electric current at point P. So applying first law of electric current at node P, we can write at point P. Actually, we get I1 is coming and I2 also coming. So entering electric current, sum of entering electric current equals to outgoing electric current, I3. This is the actually equation number 1. Now applying second law, that means voltage law of Kirchhoff's voltage law. It will be, this will be E1 this will be from the closed circuit, first closed circuit, consider closed circuit, E1 R3 R1, this closed. Okay, E1 R3 R1, this closed circuit. So applying voltage law, that means second Kirchhoff's law, we can write total EMF or voltage drop equals to E1 equals to what will be B1 plus, that means I1 R1 plus next resistance I3 R3. Okay, or E1 equals to what? 3. 3 equals to the I1 means R1 means what? 2 ohm. 2I1 plus R3 means what? 5 ohm. I2 I3 equals to first E1 means 3 volt. This is equation number 2. Again, for the closed circuit, for closed circuit, E1, E2, R2, R1. Okay. For another one, this closed circuit, we can consider what we can write. So E2 equals to what will be? E2 equals to I2 R2 plus I3 R3. That means E2 equals to what? 1.5 volt. 1.5 volt. R2 means what? 1 ohm. That means only I2 into 1 plus R3 means what? 5 ohm. 5 I3 equals to 1.5 volt. This is equation number 3. Now, after solving these 3 equations simultaneously, we get the values of all electric current here. Now we will try to solve here these 3 equations. Putting the value of from equation, putting the value of the value of I3 from equation 1, okay, in 2. Okay, so we get just putting I3 equals to what? I1 plus I2. Therefore, equation 2 becomes 2I1 plus 5 I1 plus I2 equals to 3, or twice I1, 5I1, 7I1 plus 5I2 equals to 3. This is equation number 4. Again, from 3, putting the value of I3 in equation 3 from equation 1. So I2 plus 5 into I1 plus I3 equals to 1.5. Okay. So, or we get 5I1 plus 6I2 equals to 1.5. This is equation number 5. Okay. Now, from equation 4 and 5, just I1 and I2 variable. This is why you can solve here. That means equation 4 multiply 6 minus equation 4 multiply 5. Then we get what? Multiply 6, 42I1 plus multiply 6, 30I2 multiply 6, 18. and multiply 5 with equation 5, what will be 25 I1 plus 30 I2. This 1.5 into 5, what will be 7.5. Now subtracting, this is elimination process. We get 17 I1 equals to, subtracting, we get 10.5. That means I1 equals to, we get here 0.62 approximately ampere. Okay, ampere approximately. Now putting the value of I1 in any equation of 4 and 5. Putting the value of I1 in equation 4. So 5 I2 equals to, what will be 3 minus 7 I1. Okay, that means 3 minus 7 multiply 0.62. This equals to, that means I2 equals to, we get minus 0.26. Minus 0.26. So, and from equation 1, I3 equals to, what will be I1 plus I2. Okay, I1 means what 0.62 and I2 means what minus 0.626. 0.26. So this equals to, what will be 0.26. So I3 equals to, we immediately get 0.36. Hence the value of all electric current we get, hence the value of electric current will be what I1 equals to 0.62 ampere, I2 equals to minus 0.26 ampere, and I3 equals to, what will be 0.36 ampere. This is actually example of KIRCHHOFF'S law, applying KIRCHHOFF'S law in our real life. So very easy. I hope if you practice more, you get you understand better. So thanks to everybody.